So in case of Fourier series, we transform one signal to a sum of other signals. So in Fourier series, the form looks like still we stays in time domain. We still stays in time domain. We change one signal in time domain to the other signal in time domain. Why? Because we are more familiar with sine waves. We are not so familiar with some non-sine waves. So one idea is, those guy Fourier, he has idea that, what if we change one signal to a summation of other signal, sine waves. Can we do it? Yes. In some cases. Some cases we cannot. And chapter 4 and 5, we have Fourier transform. Fourier series is only valid in periodic signal. Signal is periodic, which is often observed in engineering world. In Fourier transform, we cannot do it. This one is also applicable to non-periodic signal. In case of Laplace transform, it's more general form that Fourier transform is J based on J omega, which is inside those unit circle in complex plane. Remember in the first day, the first page of this lecture, we're starting from Euler's formula. Euler's formula describes a way to complex segmentize, separate the complex exponential into real part and imaginary part. E j theta equals cosine theta plus j sine theta. We are dividing them into real part and imaginary part. So in case of Fourier transform, we talk about both periodic signal and non-periodic signal. In both cases, we are mainly talk about on a unit circle in a complex plane. In case of Laplace transform, there are more freedom in the complex plane. They basically covers all the planes. So we are starting from time domain, frequency domain with more either complex plane. So we are broaden our views more and more. But one thing to note here is, imagine that we have certain signal and try to transform to another signal which is equivalent. Sometimes, in most cases observed in engineering world, it's true. It's very true. However, in some cases, the other form may not exist. That's the reason that the Laplace transform especially has a concept that the reason of convergence. Even though I described that Laplace transform covers all the planes in complex plane, that does not mean that they can utilize all the plane. There are certain area they can use, certain area they does not converge, which they cannot use. So let's talk about one step by step. So and then we'll close this chapter. We are finishing this lecture. That's all the semester. Also, in linear time invariant system, signals can be represented using a set of basic signals. And remember that we have a concept in linear time invariant system. Remember that in linear time invariant system, how we find the output. What we have learned in linear time invariant system is, when you have an input and output, and try to understand what happened to the output. One of the ways we did by far here is, we have the input and we learn that if you have somehow delta function, first we have somehow delta function, we can divide this system response into each component. If you have delta function, we pick each component and add them eventually to find the final value. That's how we learn it. That's very similar in Fourier series. Remember, in here we have input k, and we have a transfer function. We multiply them together, pass through the system, and get the value y at each k, add them all together to find y. It's very similar to in Fourier series. We find out the value of each component and add them. So let's have one review. Eigenfunction. Eigenvalue and eigenfunction. Eigenvalue and eigenfunction is given as when there is operator A. When there is operator A. A little bit so I can see it. When there is operator A, when you have a certain input, if you have a scalar value of lambda, this is operator, this is what? Eigenfunction. And this constant is what? Eigenvalue. So one normal example is matrix. If you use a matrix in operator, a matrix of V, 2 by 2, 2 by 1, you sometimes have an idea that they can represent it as just like this. The form looks familiar, right? It's one way we have eigenvalue and a function. If you have operator, which is how to say, sometimes referred as a system, input to the system is equivalent to that integer or constant multiplication of the input. So input to the system, this is the output of the system, for example, equal to the constant times the input. You can view it in the way like that. One example is what? The other example is what? We will have another example. Say our operator is x dx dt. Let me move this one a little bit. And I'll say our V equals xn. What is our eigenvalue? You'll say, if you put it in here, AV equals x times input times this. So if you put x dx dt, should not have x, I think, right? This is operator. This is function. So this is function to make this one like this. So if you put it here, they become like this. So operator means same to the matrix. If you put the eigenfunction as an input to a system, so this is system, right? If you put the input to the system, if you put the input to the system, they go to here. And then what happens? xn minus 1, which is equivalent to xn. So to find eigenvalue, they should be equivalent to the input times the lambda. You can view it in this way. So you'll have lambda is n. That's the answer to this problem. So eigenvalue and eigenfunction sometimes mislead. Sometimes why we doing it, we may think in this way. But this is interesting and important concept in mathematics and in engineering because we use eigenvalue and eigenfunction a lot. Because one of the reasons I think is it gives you, you can change this complex operator into simple constant value. Because these two systems are equivalent, two functions are equivalent. So you can remove this complex operator and change it to a constant value. So that's one of the reasons I think we are using the eigenvalue and eigenfunction. So let's apply this one to linear invariant time invariant system, and input is complex exponential. So let's keep this for a minute. And put a system that we have linear time invariant system x, y. How we relate the input and output in linear time invariant system? Convolution, right? So before that, we have xt, yt equals xt convolution ht. This we have used so far. And let's change it to a form like this. Say, pick this, put h tau times x t minus tau. E tau. That's convolution, right? It's convolution. And then, now, this is case that we have input of complex exponential. Complex exponential is what? We have s is complex number. S can be a times bj, for example. So this is complex exponential. Exponential in a complex form in this way. So this is a form of, so also can be represented as a form of Euler formula. And let's put it this one to here. So let's put EST. This one becomes EST minus tau. Right? And then this is what EST times E minus S tau is. In this integration, they're depending on tau. T doesn't have a relationship inside here. So we can take this out. So this one becomes EST times infinite to infinite H tau, leaving this E minus S tau V tau. Okay? Pretty straightforward, right? And then, let's find how we think eigenfunction, eigenfrequency. I'm sorry, eigenfunction, eigenvalue. Eigenfunction we often viewed as an input to the system. System is A, which is system is this linear time invariant system. The output y is this one or this, which is given like this. If there is eigenvalue, our eigenfunction is input, right? That will look like this. So if you see this, we can consider this as eigenvalue, right? So in here, this is summarized in this slide. We can consider eigenfunction as EST, which is input to the system, and the system operator is A. So if V is equivalent to this A is the system representation of this, we know that to understand the output, if this is linear time invariant system, we use the convolution to find it. After the convolution, we figure out that it looks like this form. If there is eigenvalue, then there will be input times the eigenvalue, which is constant value, which is equivalent to this. So this is eigenvalue, eigenfunction. You can view it this way. We define this one, which is this, as h. So let me erase this for a minute. This integration, which is the eigenvalue, we often call them as hs, which is they are eigenvalue which have having special value of s. So this one is function of s. Depending on s, this value can change. Likewise, in case of discrete time, we can do the same way. We can do that. We do the convolution. This is small bracket. I'm sorry, this is small bracket. And then, if you segmentize it, we can divide them as Gn times other factors. We call Hg as eigenvalue, which is have a form like this. So if you do the same thing in continuous discrete time, you can have similar forms. Right? C minus k. Which is we also say have a similar forms in here. So we have learned that there is a eigen. You can view them as eigenvalue, which is special value of S or Z, which is corresponding to integration of summation in continuous time or discrete time, depending on the transfer function of the system. So this is the response when there is input of complex exponential. In linear time invariant system, it is possible to decompose. Decompose is what? Separate one signal into subset of different signals. This is possible. So final goal, before we move on, I will show you the final goal of all of these descriptions. Is page 9. This one is what we want to have in this, hopefully today's lecture. We want to have, in the beginning of today's lecture, I mentioned that this one signal can transform to the other signal. The other signal can be a summation of different sine waves. That's what we talked about before. So, final goal of today's lecture is we try to have one signal. So, let's not consider the output. It can be input, it can be output, depending on whatever you want. It can be a summation of different signals. I once told you that it's similar to when we, in the linear time invariant system, chapter 2, we say, if you put the delta, we pick a point at each point. If you put x, we calculate each point to y and add them together. Similar to this. We find the value at each point, actually each frequency, and then add them together to find the original input. So they have a form like this. there is AK times exponential, some kind of complex exponential, which is given as jk omega 0 t. Well, if you see this, does not look so familiar, does not look so interesting, right? So let's see this one more in detail. Let's forget about this. Let's just take this out. Let's say our AK E J K omega 0 t. What is this? We can decompose. We can change this one to a more familiar form. Here, AK is constant. What is this? Cosine K omega 0 t times J sine J omega t kt. This one can be viewed as you have a certain frequency. This is your frequency, right? So this is cosine, this is sine, right? So this one can be viewed as a cosine or sine, having its own amplitude, as its own amplitude. And what is this? This one is basically having an amplitude of sine or cosine, having different frequency, having different amplitude depending on AK. Each frequency has an amplitude of AK, and view of sine or cosine multiplied by sine or cosine. You can view them like this. And also note that the frequency is not arbitrary number. I think the person taking the power electronics, I already explained in today's week, right? But I will repeat one more time. This frequency is omega equals k omega 0, which is, now k is integer. K is integer, right? K is 1, 2, 3, 4. K is not 0.7, 0.9. K is 1, 2, 3, 4. That means this omega, there will be the integer multiplication of this omega 0. That means we have something called fundamental frequency, which is omega 0. And this equation can be viewed as a summation of sine or cosine waves having different amplitude. Each has a different amplitude. Each means each component has a frequency of k omega 0. K omega 0 is, as k is integer, they have omega 0, 2 omega 0, 3 omega 0, those integer multiplication of omega 0. So they will be viewed as like this. You will have a string, fundamental frequency, 2 times fundamental frequency, 3 times fundamental frequency, like this. There will be summation of these signals, but they does not have the same peak. This fundamental frequency has amplitude of A1. This is case 1. This A2 has different amplitude, which is corresponding to A2. So the frequency 3 times omega 0, they may have, I don't know, different amplitude corresponding to A3. If you add all of these one from minus infinity to infinite, we can estimate, we can make this xt. That's the basic idea of Fourier. Fourier is actually a little bit crazy guy. I will talk about him later. But this guy have a very interesting idea that what if we decompose? What if, let's go back to page 5. What if we decompose any signal to a sum of sine waves? Then sine wave is much easier to understand, much easier to analyze. And in linear time invariant system, in the linear system, we can divide, we can calculate each component separately and then add them together in the output. That's okay. That's a linear time invariant system, right? In linear time invariant, that's okay. We don't have to process input as it is. We don't have to in linear time invariant system. We decompose to them to each frequency and process each component individually, get the output, sum them eventually to find the final output. That's okay in linear time invariant system, right? We have learned in chapter 2. So in linear time invariant system, this is a very strong tool because we change a certain signal to a sum of signals which is sine or cosine, which is more familiar to us, and then process them individually. Individually means they process by each frequency, omega 0, omega 2, 2 omega 0, 3 omega 0, process individually, get the output, sum them to find a final value. That's it. So this is similar to what I once discussed a little bit in case of frequent domain. If you remember the convolution, I say this convolution can be viewed as multiplication in frequency domain. So what if you change this convolution to frequency domain, just multiply without doing those complex calculations like shifting all of together, and then bring it back. That's one functional transformation. Make this one more convenient. In here, we decompose. We separate them into a set of signals, which is more familiar, more friendly, much easier to analyze. And then analyze them individually, add them to find the output value. That's one of the points we can view the effectiveness of Fourier series. So this is a very interesting idea. Questions before we move on? No? Really? Okay. So this is a very interesting idea that what if we just transform to such the other form of the signals, which is more familiar to us? What if we do that? But one of the questions here is this really possible? That's the first question. Second question is, what is K? What is AK? What is AK, right? That's the second question. So we will learn about that from now. So let's go back to this slide later. Page 6, let's go to page 6. This one repeats what we have claimed by far. So let's erase it. So we keep on seeing EST or maybe minus ST or EJ omega 0 KT, some kind of formula continuously. So we will have a complex exponential, which is the reason that it views as cosine ST plus J sine ST. That's the reason we started with Euler formula in the beginning of this lecture. We keep on using these forms, which is corresponding actually to sine and cosine. You can view them as sine and cosine other than exponential. So let's think about what's their function. First of all, in periodic signal, this is our goal, and just put it there. Say that in case of periodic signal, we have a period of t. What is its frequency? What is this frequency? They are 1 divided by period, that's the frequency, right? And if you multiply this one by 2 pi, then you will change this frequency, which is hertz, to radian per second. That's omega, right? That's what it defines. This one is sometimes called fundamental frequency, which is the basic frequency, the lowest number of frequency that system can have. And there is a harmonics. Harmonics is sometimes referred to as integer multiplication of this fundamental frequency. It can be 2 omega, 3 omega, 4 omega, 10 omega, those are called harmonics. That's how we do it. In here, this k, plus minus 1, plus minus 2, blah, 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 going on. And the basic idea of Fourier series is we want to decompose one signal to a sum, a set of fundamental frequency and its harmonics. So, once again, we can view this one as DC, which is when k equals 0, and DC means when k equals 0, then POV looks like that. So this one will be 1. So just A0. And fundamental frequency component A1 E J omega 0 t plus A minus 1 E minus J omega 0 t. That's fundamental frequency component. Right? They're also called as first harmonics. And then A2 E 2J omega 0 t, A3, A4, blah, 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 blah. Those are the higher frequency component. So, in many systems, we can view them as this is a DC, average, and this is fundamental frequency or first harmonics, second harmonic, third harmonic, fourth harmonic, and go on. Often, this all component view as higher frequency component because this one is omega 0, frequency omega 0. 2 omega 0, 3 omega 0 is a higher frequency than the fundamental frequency. So you can view them as DC component, fundamental frequency, on first frequency, and other component having higher frequencies. This is actually exactly same to our Fourier series. So in Fourier series, they can also view that as I want to say that there's a sine wave, some set of sine waves having DC, fundamental frequency, and higher frequency component. You can divide them like that. So let's go. Too fast? Oh. Give me some feedbacks, please. I'm feeling lonely like this. So, okay, let's move on. Like this. Let's bring a very special case. If x is real, assume that this x can be complex, x can be real, x can be imaginary, x can be complex. Assume a very special case, x is real. then what? If X is real, they don't have imaginary part, right? So conjugate of real will be the same, right? Conjugate is they make this one minus, but as there's no imaginary part, we can make that the same. So this one and star of this will be the same. Also note that, so in Fourier transform, Fourier series, we define this and try to find what's xk, what's ak. In here, what is this? Assume that we can, so this is one of the ways we prove our principle. Assume that this is true. And let's try what's AK. Okay? Assume that this is true. What is this? So we can view them as to star, make the polarity of imaginary part to be minus. In here, AK may be imaginary, right? E J omega KT will be imaginary. In here, imaginary conjugate, it's conjugate, the star of this one is what? Make the imaginary part to be minus. And in here, how we can do it? We simply add minus in here. Because if you change this one, cosine does not change, but sine changes the polarity. So we just add it like this. So conjugate this one, you can make this one like this. That's what you see in the first one in here. And you can also view them. Let's think about this AK star. AK star. It's a case value. Okay? So in case of this, you can put them like that. Right? Just simply change polarity. Let's go over this. And to do that, we have one more calculation that let's bring it a new parameter. Say that P equals minus K. Let's bring one more parameter, P equals minus K. Put it here. There will be P equals infinite to minus infinite, right? And then this one is what? A minus P star. And then K minus K changed to P, so E J omega 0 PT. And we can rephrase, because this P is just a variable, right? So we can rephrase, just change this one to just K. Just change P to K, change P to K. Right? So in here, we put a star and find the value and change this k to minus p, reverse it, and change this k to minus k to p, and just simply switch this one p to k, because this k and this k are different, right? This k, two k's are different. But we can do to make a form. And we know that AT looks like this, star of A will look like that. And in real signal, we assume that they are the same, right? To make the same, this part and this part is the same now, right? That's the reason we changed the polarity a little bit in here. But to make them true, this one should be true. That's what you can see here, right? So by far, we have drawn like this. Let's rewrite. Let's rewrite this. So this one is okay. It's okay to remove this. 예. 어차피 쓰는 순서기 때문에 원래는 작은 걸 아래에 놓고 큰 걸 위에 쓰는 게 보통이잖아요. 그러니까 실제로는 얘를 이렇게 써놓고요. 그 다음에 이렇게 바꿔요. 그러니까 순서란 게 이제 여기부터 여기까지 더하라는 의미니까 이렇게 더하면 돼요. So question was, we initially have plus here, minus here. That's how we have before. Why they shift? So this summation have a meaning that we just add from certain point to certain point. So we can easily switch. So it can be plus to minus or minus to plus, but conventionally speaking, we just put the minus in the bottom side. That's the conventional way we do it. Also, it's equivalent to that. We just say change to k to minus k. There will be a k star. Same one. So let's erase this one for a minute. And let's rewrite. Let's rewrite this one. xt equals, now we can view them as, we won't say that they can be a0 when k equals 0 plus a1 e j omega 0 t plus a minus 1 e minus j omega 0 t Here like that. So we can have tk equals 1, the case, and other high frequency component. In here, we have a set. A set that we have a k e j omega 0 k t plus a minus k e minus j omega 0 k t. Right? You can view them in this way, like pairing each other. Adding them from where? Because remember, rather than 0, plus 1 minus 1 plus 2 minus 2 plus 3 minus 3, they are all paired. They are all paired. So we can view them as from plus 0, 1 to infinite. Because if you put 1, they can have 1 and minus 1. Put 2, 2 and minus 2. So automatically, even though you adding only from 1 to infinite, it's automatically adding minus 1 to minus infinite. Right? And plus a0, because a0 is only 1 point. It is not paired. So there's only 1 point. You can view it in this way. If you compare these two, what you can view them as AK E J omega 0 KT. Doesn't change. Using this, A minus K is what? Conjugate of AK, star of AK. Star of AK times exponential minus J omega 0 KT. Right? You can view them as AK times exponential J omega 0 KT star of this. Because if you put the star, looks like, let's put the star. If you put the star over there, star of AK will come out, star of EJ omega 0 KT will come out, but star of J omega will be minus of it. They are equivalent. So you can view them as this one plus this one's star, which is, say, AJ plus A minus BJ. This is something, this is star of that. So we can remove its imaginary part, right? So this part will be viewed as, if you have BJ, if you have that, all this, if you add them, this will be the removed, this will be multiplied 2. There will be twice of it. So you can view them as real part. This is called real part of you can view them as a real part of this, which is the A, and there will be twice because 1, 2, they will be added together. And then this one still stays, and A0 still stays like that, because A0 is not paired, that's just 1. So you can view the final form in here. The xt can be DC component, 0 frequency, plus real part of this times 2. Right? I think the student who took power electronics were pretty familiar with this one. Having a DC component, fundamental frequency, a frequency component, other things, multiply 2. We can view it like this. That's first one. So in short, in real signal, if xt is real, then we can derive this relationship, ak equals minus ak star. Using this relationship, we rewrite this relationship into subset of this, and this one can be paired, Plus 1, minus 1 will be paired. K minus K will be paired. And from here, we switch this relationship coming from the assumption that the signal is a real signal. We put it here, make this, and find this one to be conjugate of original signal. If we add them, the real part will be doubled, imaginary part will be cancelled. So we put 2 in here. Instead, make this one from minus infinite to infinite to 1 to infinite plus A0. That's how it flows like that. If you see this, you can view it in several ways. If you say, remember, this AK may be, I say AK is constant, but does not mean that AK is real. Constant is not, don't have to be real, right? Like J is also constant, right? So please do not misunderstand. If you see this, okay, this is real. So AK times cosine, I'm sorry. You can mislead, this can easily mislead that AK cosine omega 0 KT plus AK J AK sine omega 0 KT. This one's two times of this one's real. So okay, so we can just remove it. And our answer is 2AK cosine omega 0 t. This is not true. Because AK don't have to be real. Maybe real, maybe not. If AK is real, then this is true. AK is not real, it's not true. So don't be misunderstood. But we still use this. First of all, if AK equals A, which is a real part, E, J, zeta K. We just phrase it like this. Any complex number can be viewed in this way, right? If so, we can rephrase this one to be A0 plus sigma K equals 1 to infinity AK, because if you should do that, those AK EJ omega becomes large AK EJ zeta K times EJ omega 0 KT, right? And then there will be AK exponential J omega 0 KT plus zeta. So now we can make those descriptions just before. We can view them as a cosine part plus J sine part. And this AK is real. AK is real. So we can remove the cosine sine part. Right? So this one can be viewed as AK times cosine omega 0 KT plus some base times 2. Right? Can be viewed like this. Of course, if we say AK, okay, it can be a real part plus imaginary part. You can view them like this. Then, if you insert this one to here, calculate that, they can be, looks like A0 times sigma can view like that. So this one looks familiar to the power electronics class students, right? DC plus cosine AH BH times sine. That's how we derive it. So basic assumption here is we have real signal. Our original signal is real. Using that, we have this form, or equivalent to this form, equivalent to this form. I forgot to. Which is, we can remove those complex exponential, but instead you can have cosine or sine, or real part, or just one cosine. If you look up our book, there is an equation for each of these. To find B, to find the C, what is that? So you often see this one compared to this, you sometimes see this or this, which is really shows the advantage of Fourier series. We decompose any periodic signal we expect. We decompose this one to DC, zero frequency, does not change, plus cosine and sine. Right? So we decompose this one to DC cosine and sine process individually because this is a linear time-based system, and then add them eventually to find enough value. Sine and cosine is much easier to process, right? That's why we, this one advantage we show, one example to show the advantage of using Fourier series. Questions? 그 앰플리튜드라고 이해하면 편하고요. 어떻게 설명하면 되죠? So the reason I talk that this AK can be viewed as amplitude is I confine the situation that AK is actually the constant, the real part. It can be real and complex. So you can intuitively think that there can be some of. So in case of this, this A will be changed to the constant value, constant real part, right? So this one is actually the amplitude. You can view them as amplitude. So I gave the example, I gave the phrase that this can be viewed, conceptually think as amplitude of each frequency because they can be transformed like this. This is true. However, in real one, I gave you just as conceptual meaning. Actually, this can be complex together. Other questions? Okay. So we have, I have sold that Fourier series is very interesting, very useful, very practical, blah, blah, blah. If you cannot find the equation, then this is useless. So let's try to find what's AK. No questions? No? So we try to find, so this is our assume that again we have assumption that this is true and try to find what's AK. Let's start with X, T, E, I think like that, right? No K. In the previous one, there's typo. In page 7, this equal is actually plus. A0 plus sigma blah. So this is plus actually, this typo. Let's start with this. What is this? We just multiply this side using this. And here, k minus infinite to infinite, ak exponential jk omega 0 t multiplied by minus j and omega 0 t. That's how we define it, right? And we integrate. Just follow it. Integrate from a period. Remember, in the beginning of today's session, I say Fourier series is applicable only to periodic signal. So in here, we already assume that xt is periodic already. So say that it has fundamental frequency of 2 pi divided by t, period of t. We integrate over one period. Then what happens? Let's rephrase a little bit. Because this integration goes to t. don't have any relation with k. So we can take this sigma to outside. You can switch, you can always switch those integration and sigma. You can take this out. And in here, we put this is depending on t. So this is depending on t. This is also depending on t. But this one does not depending on t. So we can take outside and put it here. We can do that, right? And let's calculate what is this. This is what? Ej omega 0 t, which is common, k minus n. Okay. Let's calculate that. We can view this one as integration of t, divide this one to cosine and sine using Euler formula. Cosine omega 0 k minus n times t dt plus j over a period sine omega 0 k minus n t dt. We can view them this way, right? Right? And remember, you viewed them many times in high school, I think. Integration of cosine omega 0 t over one period. What happens? If you integrate this over a period, there will be sine omega 0 t omega 0 over 1, right? Plus or minus? Plus? Minus? Okay. Let's forget about that. Let's put it here. And then there will be omega 0 over 1 sine omega 0 t minus sine 0. There we like that. This is what? Omega 0 is what? 2 pi divided by t. Definition. So t times omega 0 is what? 2 pi. So this is f, this minus this will be 0. If we have sine instead, the same. Let's forget about the polarity. It will be some kind of cosine form. Will be same with cosine 2 pi minus cosine 0. Also 0. Right? So if you have cosine some periodic signal, then they will, if you integrate over a period, they're always 0. That's the phenomenon observed here. If you see this, they are 0. Because we are integrating the multiplication of omega 0. Will be omega 2, 3, 4, it will be the same. Will be just to say 2 pi minus 0 or 4 pi minus 0, 6 pi minus 0 will be the same. Except the case that when k and n is not 0, that means there is some value inside here, they're always 0. Then this one will be 0. If k and n is equal, if they are equal, what happens? This one is what? Cosine omega 0 times 0. So cosine 0. Right? So integration of cosine 0 is what? Cosine 0 is 1. So integration cosine 0 which is 1, overall period is what? T. If you put k equals n in here, will be sine 0. Sine 0 will be 0, right? Integration of 0 is 0. So, in this special case, this one will be t. Got it? So, therefore, remember, we put arbitrary, we starting from putting arbitrary n, arbitrary number n. And this k scans from minus infinity to n. So n, I'm sorry, k scans from minus infinity to plus infinite. So if n is not infinite, whatever value, there should be some value in between. So they hit the point. So in this special case, when k hit exactly when k is n, then this one is not 0 but t. Other case is 0. So you can view them as a lot of zeros except of special case when k reaches n, then with t, it's 0 again. Right? Because there's summation. So you can view this one to be just t times a n. Right? Is it? So, makes sense, right? So you can view that as this one, wow, t equals a n. Pretty simple, right? So in here you can find a n equals, move the t to this side, t over 1 over 0 to t, xt e minus j n omega 0 t dt. This is our AK. Right? If you rephrase, if you just change this n to k, then this is it. Of course, this is not mathematical way. This is not a real mathematical way. But one way you can find what is AK. So we assume that we have this function, and then we multiply this one by this special value, and then derive it, and find out that this one is 0 except a very special case when k equals n, which is final value is this. Using this, we can find what's an equals 1 divided by t over a period xt e minus j k omega 0 t. That's how you find it. So that's the final value over here. Please note, one more thing I would have to rephrase it. I gave a special case that's 0 to t. But remember, it can be any period of t. Because to make this one 0, we have cosine something minus cosine something, for example, after integration. We have 2 pi and 0 as an example. But as there is a period, we always have formed that if you have certain t, certain point t0, there will be period plus t0 minus t0. Those forms. So whenever this period is, as this one period, what is the definition of period? This one becomes same to here. So it's any value of any starting value, this one always 0. Therefore, you can view them in this way, this is another form. However, you can select any period of t. It can be 0 to t, minus t divided by t by t like this, or minus t to 0. Any period, any spacing of t, this one is true. So this is our Fourier series. What is AK? So in short, this is what I showed in the beginning of today's lecture. we want to have this form, and we derive what is AK. And if you can find AK, you can find this one, right? And that's it. One thing to note here is, it's very interesting actually. You always have some kind of pair. In here, I mentioned that you will see J omega 0 KT or ST a lot in this lecture. You can see that JK omega T, JK omega 0 T still a lot in here. They're always paired in Laplace transform, Fourier transform, Fourier series. It looks like they're always paired. In general form, to find the original signal, they are plus. To find the amplitude, they are minus. And they are switching each other. This. Okay? So you just remember three things. Just to memorize it, just remember three things. First, has a form like either this or this. Second, original form usually have plus. To find the amplitude, amplitude is already rephrased form, but to find the amplitude each one, you have minus on there. So always plus and minus pair. And they switch each other. If you remember those three things, you can easily remember many equations.